Today we are going to learn about Python Global Interpreter Log GIL and we'll see architecture, implication and solution. Let's go to next slide. Let's first understand what is GIL. GIL is a mutex in C Python that ensures only one thread executes Python bytecode at a time, even on multi-core CPUs. In short, if I say Python threads exist in our system, but only one can run Python code at once. Why does Python have a GIL? The GIL exists mainly for simplicity and performance of the memory management. It is only simplifies the execution process and perform a best memory management without any complex implications and all those things. And the key reason behind the simplicity why GIL was introduced in Python to have simplicity and performance of the management, because there are some key reasons. First is reference counting. C Python uses reference counting for garbage collections. Multiple threads want to make change of a Python object at a same time, then it create complexity and the memory management issues. That's why the GIL was introduced. Like updating reference count from multiple threads would require fine-grained logs everywhere. Like if we want to run multiple threads and without GIL limitations, then it requires multiple logs which of the one thread can change the same object, and the other thread won't be able to change the same object at the same time. So there are lot of logs we have to implement, and because of the implementation maybe the process would go slow as per our expectation if we remove the GIL limitations. And the second thing is faster single threaded performance. Without the GIL, every object access would need locking. The GIL keeps most Python operations fast and simple. That is the reason why GIL was introduced in the Python interpreter. So we can see the acronym Global Interpreter Log and the type mutual exclusion objects, and only one rule, only one thread executes bytecode at a time. Let's go to the next slide and see the necessity of memory theft. We can see the purpose. Simplifies memory management in C Python. We have already discussed this. Prevention stops race condition in reference counting. Like if we have two threads, then two threads are in a race. If without the GIL, if we implement two threads, then it will always do a race and want to change or make changes in the reference counting simultaneously, and that is the race condition. To prevent this kind of race condition, GIL was introduced. Risk without the log simultaneously. Access could corrupt object state. Without GIL, multiple threads can make change the reference counting simultaneously, and it could corrupt the Python objects. What is the benefit of the GIL? Removes need for fine-grained locking on every single object. That is the best benefit I have seen of GIL. Let's see how the execution flow in GIL. GIL manages the memory states and the execution flow. Like if we can see there are two threads and one thread will run 0 to 10 seconds, and the second threads when the first thread stops and at 10 ms seconds the context has been switched, and the second thread was running from the 10 ms to 20 ms, and then again a context switching was performed, and at 20 ms to 30 ms the thread one was completed during this time. So this is how GIL manage the execution flow. Let's go to the next slide and see the bottleneck of CPU bound tasks. The bottleneck of CPU bound tasks. First, let's understand what all the scenarios where CPU bound tasks, number crunching, image processing, matrix multiplication, all these are the CPU bound tasks. And what is the impact? The lock is held during the entire calculation. If we are doing some image processing, then we could not use the multi-threading system because it is the CPU bound task, and the lock is held during entire calculation. Consequences: multi-threading adds context switching overhead without adding parallelism. Performance often degrades. Let's see the exceptions. Input output bound tasks. Let's again, we have two threads, thread A and thread B, and thread A running for 0 to 15 ms, and then it goes for the network request or database query. During this time, the GIL log was released, and the thread B was running from the 15 ms because GIL now context switch to the thread B, and thread B complete their task, and thread A while thread A is waiting for their network request. So scenario, waiting for network file system or database, where we can see these are the input output bound task mechanism. GIL is effectively released while waiting for input output. Consequently, other threads can run while one waits. High concurrency is possible in this scenario. Let's see the evaluating the trade-off between single thread or multi-core parallelism. Single thread provides the stability and speed, while multi-core system provide the true parallelism. With help of the single thread, we are getting some of the benefit like the speed and the stability, and when it perform best when we have proper input output bound task. Let's see the benefits of the GIL design. Fast and simple memory model, easy integration with C extension libraries, high performance for the majority of scripts, excellence for input output heavy workloads. Let's go to the next slide and see escaping shared memory. If we are talking about the multi-threading and the multiprocessing task, then in the multi-threading we have multiple threads, and all those threads use the shared memory space. And if we are talking about the multiprocessing, each process has there its own GIL and the memory space, and it is perform the true parallelism. This is the difference between threading versus multi-threading. Strategies to overcome limitations. Use multiprocessing or processful executors spawn separate process to utilize multiple CPU. C extension offload heavy calculation to C library. This library often release the GIL internally. For high concurrency network task, use async queue efficiently manage waiting times without having threaded. So these are the strategy how we can avoid or overcome the limitation of the GIL. So these three are the main strategies we can use if we want to implement a efficient solution in the Python language. So one of the questions that arise when we select the right model. First, check out your goal. What is your primary constraint? If it is an input output bound task, or if it is a CPU bound task. And if it is a input output bound task, then use threading or async. And if it is a math, image processing, ML, CPU bound task, then use multiprocessing. Performance depends on matching the architecture to the workload. Okay, now I have in my Visual Studio, and we'll see Python global interpreter log with complete scenarios where we can see CPU bound versus input output bound task, threading versus multi-threading, async IO, GIL behavior and limitations. We are importing some of the libraries to perform this task. For the async task, import async multiprocessing, import threading for implement the threading related task. And I have created a timer function that is a decorator function, and we'll see the time for each and every function that we are going to run in the next cells. Okay, this is kind of a decorator. Like we are using this decorator at the function, and this decorator will going to print the time. And here we have implemented the single threaded CPU bound task, and for the single threaded CPU bound task, it takes 0.19 second to execute. And here we are going to implement the same task with help of the multi-threaded CPU bound task, and it takes 0.19 second, and both of these CPU bound tasks, that's why it takes the same times. Then it doesn't matter whether it is single threaded or multiple threaded. And we are gonna see that GIL bottleneck, even this is a multi-thread system, still it takes 0.19 second, as same as the single thread system. Multi-thread system with input output one task, the same task we are perform. Now we have implemented a slip that is the input output bound task. It is sleep for 2 seconds. It means wait, it is in a waiting state in 2 seconds. That's why it takes only 2 seconds to perform this task. Multiprocessing CPU bound task, this is a true parallelism, and it takes only 0.13 seconds to perform the same task.